Good morning and welcome you all for today's class. Yesterday we have discussed about psychrometric properties and we have solved one problem based on psychrometry, how to find out from given value, how to find out other psychrometric properties in mixing up the air problem. And today we are going to discuss about finding out sensible load and latent load calculation by using psychrometry and how we define sensible load and latent load and also sensible heat factor. Sensible heat factor, because this is a topic that we are going to discuss, is most important in sense that all cooling load and heating load calculation you will find that sensible cooling or heating load or latent cooling or heating load, everywhere these terms are used, and these terms are used for the finding out cooling and heating load calculation. So, so now starting from defining what is a sensible load and latent load. So let us draw a diagram. First, this is a block diagram of the psychrometry chart, and I will define sensible load here. So any process here, any process is occurring. That is process A to B and B to C, A to B and B to C. And correspondingly we have to define, and due to mixing, correspondingly we have to define here, this is a scale of the absolute humidity or specific humidity. So here it is omega C and it is omega B, and correspondingly we have to define enthalpy from enthalpy. This is enthalpy scale. So here you will define, this is enthalpy HC and this one HA, and here corresponding to point B it will be HB. These are enthalpy, and suppose MA is mass, because in air conditioning problem MA mass of airflow, mass of dry air. We have taken mass of the airflow required for the air conditioning, because we know that the working fluid for air conditioning is air itself, and coolant is which air is a working fluid and coolant that is used is refrigerant in a cooling coil, and other things also there for humidification, what is required, humidification and dehumidification. So working fluid for air space cooling is air itself, and quantity of air that flow inside the room from inside to outside, from outside to inside, and mixing will take place. So air is a main. So air flow rate is given, m is mass flow rate, and cm is also cubic meter per minute. Because in air conditioning problem, your working fluid is given, flow of working fluid is given cubic meter per minute. Generally, it is defined as cubic meter per minute. So here, first process is A to C, but it is occurring in two steps: A to B and B to C. A to B, according to psychrometry chart, A to B, because these are this is a vertical line TA and TB. These are dry bulb temperature. At condition A, dry bulb temperature is TA. At condition B and C, dry bulb temperature is TB. So in this process, because A to B, temperature is increasing and moisture content remains constant. Here you can see in this line, A to B or B to A. A to B, temperature is increasing means sensible heating, and B to A will become sensible cooling. So what will be sensible heat? We define QS. QS is a sensible heat. You can simply define, because mass flow rate is A, you can take mass flow rate is A, MA, and there is enthalpy, specific enthalpy are given HB minus HA. So this is according to enthalpy, because HA, HB are specific enthalpy, kilojoule per kg, but here mass flow rate is given from A to B and from B to C is MA. So sensible heat load will be equal to QS equal to MA, mass into specific enthalpy difference. That will be equal to MA. You can define CP TB minus CP into TA. That is equal to, you can take MACP common. CP is a specific heat of air in kilojoule per kg Kelvin, and this is a TB minus TA. TB minus T, that is temperature difference between point A and B. So this one is equation for finding out sensible heat. But actually in actual problems are given in terms of mass air flow. Because working fluid is air and it is given question that question in actual problems cubic meter per minute. Flow of air is cubic meter per minute. So what will be MA? MA equal to cubic meter per minute if divided by 50 then multiplied by rho. Rho is density of air. Cubic meter volume into rho equal to mass upon 50 cubic meter per second. Then it will become mass equal to V volume V into rho. V is a cubic meter per minute divided by 50 cubic meter per second into rho, that is a mass in kg. So putting this value mass in this equation, cmm rho into Cp upon 60 into Tb minus Ta. And this value we have to define because these are values and these values may vary but not there is a significant change in values. If we take phi, relative humidity around 50%, 50% to 60%, and temperature, drivable temperature around 20 to 30 degrees centigrade. You can take these values. Cp you can take 1.0206 and rho will be around 1.2 kg. These are values for given conditions, and for refrigeration, for air conditioning, almost air conditioning we will take under these conditions. So we can take Cp equal to 1.0206 and rho equal to 1.2 kg per meter cube. So making this equation more simple and more empirical that you can easily remember, because in the actual problem you can use these ready-made equations and it will make easier for you to solve the problem. So Qs equal to cubic meter per minute. This is given, always given in question, and rho equal to 1.2 and Cp equal to 1.0206 upon 60 and equal into Tb minus Ta. So solving these numerical terms, reducing these numerical terms, equation further simplify 0.0204 cubic meter per minute into delta T. Delta T. Delta T is a temperature difference, Tb minus Ta. So this equation you can easily solve. So you can easily find out, and this value you will get because you have taken cubic meter per minute to cubic meter per second. So mass flow rate is kg per second, and all values you given. So this equation you will find in kilowatt of sensible load per second. Sensible load, what is per second sensible load? This equation you can use for finding out sensible load in any process, whether it is a cooling load or whether it is a heating load. It is always you can use this equation. This equation you can always use. And next one is, so this equation I will write here, sensible cooling load. Qs equal to 0.0204 cubic meter per minute into delta T. So this one is a sensible load. Cooling load or heating load, both values are same. Next one is a sensible latent load. Latent load, that is a process BC. That is a process BC. In process BC you can see. In process B to C. In air conditioning problem always accompanied with sensible load and latent load, because some humidification and dehumidification also required. When you are reducing temperature, condensation will take place, and so moisture will be removed and you are heating, some humidification required. So in both process, whether humidification or dehumidification, sensible latent heat will be either added or removed. So that latent heat you have to calculate by using process B to C. What will occur in sensible process B to C? So you can see here QL is the latent load of the building. So QL equal to, again mass flow rate is same, MA into HC minus HB. HC and HB. HC is a final enthalpy and HB is a initial enthalpy. Now you break this as SC. MA into SC. What is included in SC here? CP into temperature, Cp into temperature, Tb, and plus there is one more thing that you have to define sensible latent load. There is a moisture content here because moisture is changing from B to C. Here omega B and here omega C. Moisture is changing, so moisture transfer will take place. So here another energy will be HFGO, that is latent heat. The water at 0 degree centigrade. And what is a fraction? Here fraction is omega. Omega B is a moisture content, kg of water vapor per kg of dry. That's why we have multiplied by, because omega B part is there is a vapor. So for that this latent heat is required to convert water into moisture. And minus at HB, here we have taken SC. That will be taken C term will come first, SC minus HB. And second, HB will contain Cp into Tb and plus HFGO omega B. So you know that for this point B and C, Tb equal to Tc. Tb equal to Tc, because temperature remains constant. Tb equal to Tc. Tb equal to Tc, temperature remains constant. So you will take here this term, you will remove Tb equal to Tc. So only term will remain HFGO. HFGO for water at 0 degree centigrade is equal to 2500 kilojoule per kg at constant temperature. At 0 degree centigrade, if you convert water into moisture, it is HFGO, and this HFGO also same for both. So Ma into HFGO, and remaining terms will be that will be equal to omega C minus omega B. Omega C. This is a moisture change in moisture content, because from B to C there is a moisture is increasing. Moisture is increasing from B to C. So moisture increase will require latent heat of enthalpy. That's why at every point at B and C we multiply by latent heat of the vaporization HFGO, and this will be equal to, here you can put value 2500, because this is the latent heat of the phase transformation into Ma into omega C minus omega B. So this is for the, and you can also, this term is also known as Ma into G. G is moisture transfer. So you will, I think I would not like to confuse you here. So 2500 Ma into omega C minus omega B, that is a latent load QL. Further you simplify in terms of, because here earlier in sensible heating load or cooling load we have taken cubic meter per minute. Same thing applies here, cubic meter per minute. So cubic meter per minute. So putting values up here, Ma equal to cubic meter per minute into rho upon 60. So multiply by this equation. QL equal to 2500 into Cmm into rho upon 60 into delta omega. Here delta omega we have taken omega C minus omega B. Final moisture final absolute humidity minus initial absolute humidity. So simplifying this equation, putting value already in case 1 we have taken rho equal to 1.2. This rho remains constant. So 2500 into Cmm into 1.2 into delta omega upon 60. Solve this equation. So you will find around this value. With this value, cutting this value 50 and 50 again here. So QL you find 50 into Cmm into delta omega kilowatt. This value is also come in kilowatt. So now this one is easy. This one is easy to remember. Cmm constant for sensible load, because same air is flowing from A to B process. Because we have broken this AC process in two parts, sensible load and latent load. So flow rate is the same, cubic meter per minute. So in terms of flow rate, you have derived this equation. We have derived this equation. Now total load. What is total load? Q total. Q total equal to Q sensible plus Q latent. Q sensible plus Q latent it is a total load. So total load equal to 0.0204 cmm into delta T and plus 50 cmm into delta omega. That is a kilowatt. That is also in kilowatt. So that here I want to define one term that is known as a sensible heat factor. Sensible heat factor. What is sensible heat factor? It is a ratio of sensible heat to total load heat. How much? What is a fraction of sensible heat in air conditioning process of building or space? What is a fraction of sensible heat to total amount of heat? This ratio is known as a sensible heat factor SHF. So that term I want to define. Sensible heat factor is defined as sensible heat QS upon QT. QS upon QT is known as a sensible heat factor. SHF you can define here. QSC already we have defined 0.0204 cmm into delta T upon 0.0204 cmm into delta T and plus 50 cmm cubic meter per minute into delta omega. Dividing this equation numerator and denominator by the numerator, so you will get 1 upon 1 plus 50 upon 0.0204 delta omega upon delta T. So dividing this, solving this value, you will get equation 1 upon 1 plus 2451 delta omega upon delta T. See from this equation, this one is a delta omega and this one is a delta T. So what is delta omega upon delta T? It is a delta omega upon delta T. It is a tan theta. You can write here a tan theta. That is equal to 1 upon 1 plus 2451 tan theta. So further you can get equation in terms of the tan theta. What will be tan theta? From this equation you balance this equation. SHF equal to 1 upon 1 plus 2451 tan theta. So tan theta equal to 1 upon 2451 1 upon SHF minus 1. This is a most standard equation for defining sensible heat factor SHF. Tan theta is the slope of the sensible load upon latent load upon sensible load. So this sensible heat factor you can define if this part is known as sensible heat factor SHF and this part will be equal to 1 minus SHF. This one is a sensible heat factor SHF. 1 minus this part remains 1 minus SHF. And this, I think today's discussion clear your concept about sensible load and latent load, and these are two most important terms of the air conditioning. If you understand these two terms, then cooling load, heating load calculation become very easy. And in next class I will discuss about bypass factor. This concept will apply for bypass factor also. Bypass factor and cooling coils. Bypass factor and cooling coils I will discuss tomorrow. So for watching today, thank you very much. And if you like, please comment and subscribe and also share to your friends. Thank you very much. Have a nice day.